Okay, I'm back. And so before we talk about what the energy is associated with gravity, let's go back and talk about in more detail about the gravitational field, G. Where does it come from? So can we have a formula that we could use to actually calculate the gravitational field? So this was our formula that we came up with. The force of gravity was equal to the gravitational field multiplied by a mass that was being put into that gravitational field. So this m is this m up here. It's a mass that's going to be placed into this gravitational field that's created by this thing here. So let's see if there's a relationship between this and something up here. So this is the formula for the force of gravity, minus big G, a fundamental constant of the universe, and then m1, m2 divided by r squared. So if you consider m1 to be the planet, so m1 is going to be the mass of the planet, and then m2 is going to be this mass up here. So if I want, I could just erase this. Okay? So we could look up on the internet what the mass of the Earth is. And so that would be this thing right here. So if we were to look at everything that's inside of that circle, that is the gravitational field. And then notice you have this m is that m right there. So we could actually compute the gravitational field of the Earth at any distance from the center of the Earth. But what would be the gravitational field at the surface of the Earth? Well, we would find this distance here from the center of the Earth to the surface would be the radius of the Earth. So if we took the radius of the Earth and squared it, we take the mass of the Earth, and then we know what big G is, so I gave you that number, and we calculate all of that put together, you get a special number. And the number that you get is 9.8. So what little g is it represents the gravitational field of the Earth at the Earth's surface. So it's just a special, this one is a special example of the normal gravitational field of the Earth. And as long as you're close to the Earth's surface, we mentioned that even when you're like 400 kilometers up, it's still within 80% of its actual, of this number here. So as long as you're close to the Earth's surface, you can use little g in those formulas. And so instead of this, we could say that it's minus g m, and then we could take this and flip-flop it, and we could say that this is minus mg. And do you remember that that's weight? So the weight of an object is its mass multiplied by little g, which was 9.8. So now we know that this is the mass of the object multiplied by the gravitational field of the Earth when you're close to the Earth's surface. So this down here, so this is the approximation for the force of gravity when you're close to the Earth's surface. I wonder if we could do it for energy, and yes, we can. So one of the things that Sir Isaac Newton came up with was based on the formula for the force of gravity, he calculated the energy of gravity. So this is gravitational potential energy, and look at how similar it is. It's got a minus, it's got a big G, it's got an M1, M2, but notice it's divided by R. So it's not divided by r squared. But that's the only difference between the force of gravity and the energy of gravity. Okay, I wonder if we could simplify that formula when you're close to the Earth's surface. And yes, you can. So that formula there for the potential energy of gravity simplifies into just mgh, where h is the height above the Earth's surface. So in this picture here, h would be this distance from here to here, and then this is where you'd put your other m. So that m would have a certain amount of potential energy because it's a certain height above the Earth's surface. And so we end up with that formula, and that should look familiar because just a few lessons ago we talked about energy, and one kind of energy was potential energy. All right, so let's put this all together here. You have the actual formula for the force of gravity. So that would be force of gravity equals minus big G m1 m2 divided by r squared. But then you could approximate it as just being mg, where little g is the 9.8 thing. Similarly, the gravitational field script g becomes little g when you're close to the Earth's surface. And then that complicated formula for gravitational potential energy simplifies to mgh, again, when you're very close to the Earth's surface. All right, if you're one of my students, don't worry about having to actually calculate the potential energy of something using the complicated formula. Now you should be able to use the mgh one. So that's going to be on the exam. Got to be able to use that one. But the top one is going to be very, very important when we start talking about the orbits of objects and when we start talking about Kepler's laws of motion, which happens to be our next subject. So I'll see you in just a moment.